Hey, hello everyone. Our next speaker is Professor Christian Blanchet from Université Paris-Cité and Sorbonne Université, and he's going to speak to us about the homology of configurations in ribbon graphs. Professor, whenever you're ready.
Okay, thank you. So it's a pleasure for me to give a talk in honor of the birthday of Lou. I will not tell you as much as history compared with Joseph, but I will mention how much, as a quantum topologist, I'm indebted to Lou. So first, I want to say that I put ribbon graphs, but this is mostly homology of configuration in surfaces. And a main part of this talk is joint work with Martin Palmer, who is here, and Avais Shokat from Pakistan. And I will complete with the story of ribbon graph, which I wrote for a book dedicated to Norbert Acampo. So the question motivating this program, is quantum versus classical. So as we know, from algebraic topology, you get a classical invariant. For example, the Euler characteristic, homology, torsion, Alexander polynomial. And in knot theory, from von Jones, we know about quantum construction. So that we have a lot of quantum invariant, including of the Jones polynomial, colored Jones, on-fly PT, Joseph talked about, Reshetikhin-Toureyev invariant of three-manifold, TQFT, link homologies. So, and here I want to mention Lou Kaufman, who came with a nice state model for the Jones polynomial, which we used a lot. So he was great in popularizing what became quantum topology. And I suspect he was probably the first to write quantum topology in a title. He wrote in 92 an introduction to quantum topology, and then he published a quantum topology book. So I'm not sure to whom we should attribute the terminology quantum topology, but I want to say that with Von Jones, Witten, Reshetikhin-Toureyev, and others, he is among the founder and promoter of quantum topology. So my program, my question, I start motivating the work here is quantum topology. Can we get quantum topology inside classical algebraic topology? And in introduction, we know from the beginning that part of the story is connected with algebraic topology. So we start with classical braid groups, pi1 of configuration of points, unordered configuration of points in the disk, and which happen also to be a mapping class group for the punctured disk. And what Ruth Lawrence did in 90 is a family of representation from the classical braid group to the linear group of homology of a covering space, a Z2 cover, in fact, for unordered configuration in the punctured disk. So here the tilde is a Z2 regular cover of the unordered configuration space of n distinct points, unordered, in the M punctured disk. So in some sense, so this was classical topology. And now, connected to this, we have this famous theorem everybody know from Bigelow and independently Kramer, Stephen Bigelow, in 2001-2, which is that the braid group are linear. You can embed the classical braid group in a matrix group. And Bigelow proof is that this L2 essentially is that this Lorentz representation, in the case n equal 2, is faithful. And now this is connected with quantum. In fact, it was proved by Kono and Jackson-Kerler independently that, in fact, the main step is probably due to Kono previously, that this Lorentz, which we call LKB for Lorentz-Kramer-Bigelow representation, are equivalent to SL2 quantum representation acting on highest weight spaces. So I just want to say that you understand or not, but this is quantum. It's known that this Lorentz representation are quantum. So now we start the first section where we go to surface configuration. So the goal would be to define and study LKB type representation for the mapping class group from homology group on a regular curve of the configuration space of n point in a surface sigma. In my talk, sigma will have genus G and M boundary component, and M is positive. There is a story for closed surface, but it's a little bit different. So this is my model for the surface sigma JM, and I want to describe, in order to define a regular curve, I want to describe pi1 of the configuration space, which is called the surface braid group. So the 3 dots here hold for the base configuration. So in my picture, I considering configure n equal 3. And I put the alpha I, beta I for the generators of pi1, but by moving only the first point, this also gives a braid. So in the braid group, we have pi1 generators, which I depicted alpha I, beta I, and the classical generator coming from inclusion of disk with points. So now there is the representation for this braid group is less known than the classical one, but there is a very nice presentation worked by Paolo Bellingeri. And I should say the first presentation was by G.P. Scott, and it was revisited by Juan González Meneses. And the one I'm formulating here is from Paolo Bellingeri. And so we have here the pi1 generators, 2G pi1 generators, corresponding plus m minus 1 because I have boundary component. And then I have classical generators, sigma 1, sigma n minus 1. If you want to think that n equal 2, you are welcome, you will understand. Then you have only sigma 1, and that's it. And you have the braid relation, which you know, BR1, BR2. And then you have commuting relation. I do not insist too much on this commuting relation. It's a little bit of work to establish, to see this relation and then to show that this is complete. But I just focus on the special commuting relation for the reason that this relation is not homogeneous. And I will not have time to draw this relation, but it's a good exercise. In this picture, I use the previous model with composition written from the right, which is not always common, but when you do with local system, this is convenient. So now, if we consider quotient of surface braid group, because we are interested in connected regular curves of the configuration space, and they are associated with quotient maps from the surface group to your preferred group G. In the case of Lorentz, sigma was the disk, punctured disk, and G was Z2. And essentially, the question was extracted from abelianization. We could already consider the trivial question, meaning the usual homology. And this was studied by Moriyama and in 2007. And he proved that this recovers the known Johnson filtration. So I will not consider this case, but I want to mention this work by Moriyama. I just want to mention that we could also abelianize, and so probably many people tried, but this is not so good for the reason that if you abelianize the surface braid group, you get the homology of the surface up to a Z2 factor. So meaning that configuration will not bring you much more than the surface. So then the idea we get for a replacement of abelianization is the Heisenberg group quotient. So we started with an easy result with Martin Palmer, Aves Chocat, which is that if you quotient the surface braid group by commutator with sigma 1, meaning that you force sigma 1 to commute, then you get a quotient with this, which is the central extension of the homology, known as Heisenberg group. So you get as a quotient this Heisenberg group, which is a Z times H1 as a set, but with group law Kx times Ly equal K plus L plus X dot Y intersection, homology intersection, and X plus Y. We should say that essentially the result was new for n equal 2, because Bellinger, Gervais, and Waski have identified the second nilpotent quotient of the surface braid group as the Heisenberg group. I just point out that we put different relation, focusing on the fact that we are making sigma 1 central, but for n greater than 3, essentially this quotient was known. So now, these Heisenberg homologies. So from the quotient map we just defined, we get the Heisenberg cover of the configuration space. There is an extra bracket here. And we can show that action of a mapping class lift to the Heisenberg cover, meaning that the kernel of phi is respected by the mapping class, meaning that we have an action on homology. The one question is, what is this homology? And I will come not to the native homology, but to variants later with computation. Here, I just first want to give you the structure. So we know that on the covering space, we have a deck action of the group, and this will make the homology module, right module, because I'm writing on the right with my convention, on the group thing of the Heisenberg group. And if we think a bit about this, the action of a mapping class is twisted over this action by an automorphism. If you think about the situation with covering space, this is not very difficult to understand, but this is a priori a difficulty because if we work over the bracket H, we do not get an action which will be linear over the H, but twisted linear. So what we can further do is take a representation of the Heisenberg group acting on a finite or infinite vector space. And then by composing with phi, you get an homomorphism from pi1 of the configuration to a linear group, which is exactly what we need for defining homology with local coefficient in V. Then we can consider homology of configuration of endpoint in the surface with a coefficient in a module over the Heisenberg group, in a representation of the Heisenberg group. And here there is maybe a subtle but quite interesting remark, which is in the case where the representation rho is good, meaning that if we twist with FH, or with an automorphism of the Heisenberg group, we canonically, or canonically up to scalar, get a representation which is isomorphic to rho, to the initial one. Then we can cook from this a native representation of the mapping class group. In the case where it's up to scalar, we get a projective representation of the mapping class group, which means a representation of certain extension, central extension. So we have a notion of good representation, which allow to have an action of the mapping class group on homology with coefficient in a representation of the Heisenberg group. And here, I will give you an example we have in the paper with Martin and Avais, which is not the usual model for representation of Heisenberg group, but which is good. And the point is that on the group, on the Heisenberg group, we can define the left regular action. And it happens, so the formula for this left regular action, send kx to k plus k0 plus x0 point x, and x plus x0. And this is an affine action. And an affine action, this means that we have an homomorphism from the Heisenberg group. Sorry, it should be GA to GA of Z to G plus 1. It should not be GL, it's GA. But if we add an extra factor, we will homogenize and get an homomorphism to linear group with one rank more. And the formula is given here. This linearized translation action sends the extra parameter nu, comma kx, to nu, k plus nu k0. So we make it linear by using nu. It's almost a course in elementary linear algebra, affine and linear algebra. The point is that this action is good. Then we obtain a native untwisted homological action, a representation of the mapping class group acting on homology with coefficient in this finite dimensional representation. And my question was classical versus quantum. Here I will mention a strong result by Marco de Renzi and Jules Martel. If Q is a payload of 1 for odd P, we can consider the modulo P Heisenberg group HP, which is the same construction as before, but with center Z over PZ, and replace H1 by H1 mod P. And it happens that it has a finite dimensional, I should say, Schrödinger representation. It has an irreducible unitary representation, WQ, where U equal 1 dot, so my generator of the center, acts by Q. And it is unique up to scalar. So coming back to my previous comment, from this, we get, so this representation is a finite dimensional version of the famous Schrödinger representation, which could also be used. And using this representation in the case of surface of genus G with one boundary component, Marco de Renzi and Jules Martel, they obtained one, an action of quantum SL2 on a sum of homologies, and second, inside this sum, a sub-representation isomorphic to the Gth tensor power of the adjoint representation. And this is a projective mapping class group action known in TQFT as Kerler-Lyubashenko non-semi-simple TQFT representation. So inside this construction, if you specify this finite dimensional Schrödinger representation, you recover certain quantum representation. So you should think about this as analogous to the theorem I mentioned by Kono and Jackson-Kerler, but for the mapping class group now. So this was the first part. Now you could tell me, yes, but what are you able to compute something? And there are two questions. One question is compute the homologies, and second question is compute the mapping class group action. So in this paper by Marco de Renzi and Jules Martel, they are proving by computing. It's not easy to handle, but they really compute. So it's if you like computation, you can go to their paper. I will be more sketchy on the description, but I will give you certain elements. So now I go to a ribbon graph. So a ribbon structure on a finite, we will recover surfaces immediately. ribbon structure on a finite graph, gamma, is a cyclical ring of the adjacent edges at each vertex. And from a ribbon graph, you build a compact-oriented surface containing gamma as a strong deformation retract, and it's obtained by gluing bands according to the ribbon structure. And I give you a very easy example where you glue 3 bands and you get genus G with 1 boundary component with the standard model. So now you could also consider the braid group of the graph, defined similarly. And by inclusion, this group goes to the surface braid group. You should be careful because if you the surface braid group depends on the ribbon structure, while the graph braid group doesn't. So, for example, here you have the theta graph, and with the theta graph, you could also have genus 0 with 2 boundary components. But nevertheless, you have a map. And now my goal would be to compute homology of configuration with a local system, with local coefficient V, from the graph gamma plus ribbon structure. And then because we have a map on pi1, a local system on configuration in the surface induces a local system on the subspace of configuration in the graph. So it makes sense to use V as a local system on the graph configuration. And now I will state a quite strong result, which is called the compression trick, and I think it's due to Stephen Bigelow. And this will work for not the native homology, but for Borel-Moore homology and cohomology with compact support. So the Borel-Moore homology is defined as inverse limit relative to the complement of a compact subspace. And the cohomology with compact support is cohomology with similar direct limit, but also relative to the complement of a compact space. So we are interested in those variants. I will tell you why this compression trick works in this case. So following a so-called compression trick, first used by Stephen Bigelow, we can prove the following, that the inclusion of configuration in the graph into configuration in the surface induces for a representation ρ, for example, of the Heisenberg group, but it could be of the braid group. We get an isomorphism on Borel-Moore homologies. So we can compute Borel-Moore homology with the graph, provided we use the restriction of the local system. And same for cohomology with compact support. So the proof of the theorem is an improvement of Bigelow proof. The subtlety is that we know that the surface deformation retract on the graph. But when you do this on configuration, you will get collision. And so the trick, I will not write the whole proof, but I almost could. The trick is that you use deformation retraction to an epsilon neighborhood of the graph, and then you claim that you can avoid the collision locus. So you get configuration which will not be, which will give equal value, equal points when you go to the graph. And you can make excision to this. And in fact, generally, you teach that excision gives you an ISO in homology, but if you are careful, you get an homotopy, in fact, an homotopy equivalence. So when you compose this, you can prove this theorem. So this theorem is retraction, deformation retraction, and excision. The subtlety is in excision. And if I want to give explicit, quite simple result, I will go to a relative version of this. It's not even, I mean, I will tell you something afterwards, but it's good to have a relative version where you take a finite graph, you take a subgraph whose component AI are oriented curves, not necessarily closed, it can be intervals, and we put a compatible ordering of the adjacent edges at each vertex. If you have no AI, it's a usual cyclic ordering, but if you have AI, and it will be more clear with this, you see that here you take the rotation this way, and the outgoing AI is first. We want that the component of AI give you oriented part of the boundary when you do a regular thickening. And for this regular thickening, for the specific edges in A, you take half band rather than two bands, rather than the full band where the graph is in the middle. So my compatibility condition is just that I want this outgoing to be first, 1, 2, 3, and here it should be last, 1, 2, 3. Outgoing first, ingoing last. This is exactly the compatibility condition, and the same proof works as well. This means that we get a compression trick in the relative case. Here, there is a notation saying that when I put configuration of endpoint with a pair, it's the subspace of configuration in X with at least one point in Y. So if Y is in the boundary, so this will be part of the boundary in the configuration. And then we have a similar theorem, which is an ISO in Borel-Moore homology between the configuration homology Borel-Moore of configuration in the graph gamma part of the boundary, and same for the surface, configuration of endpoint in the surface, gamma point in the boundary. And it should be Borel-Moore, and as well for cohomology with compact support. And now, let's say an easy case. No, about the computation. So there are many papers for computing homology of configuration in graphs. And usually not with local system, but it's easy to adapt with local system. And if you do not take Borel-Moore, it can be obtained from a combinatorial model. sorry. It can be obtained from a combinatorial model if gamma is enough subdivided. So you have a condition. In fact, this condition will allow you to remove safely a boundary of the diagonal in the symmetric space so that you get the same homology. So this is known. There are many works for computing usual homology or homology with local coefficient, but not the Borel-Moore one. And in fact, for Borel-Moore, it's even easier because we may work with a finite open cell decomposition, which does not confer a CW complex structure, but nevertheless gives a filtration which works similarly for computing Borel-Moore homology. So you should think that, if I'm very brief, you can get Borel-Moore homology as CW complex homology with a slight modification of the CW complex structure where you take open cells. And in very small case, if n equal to, I have 2 points, then the 0 cells will be pair of vertices in the graph. We assume at least 2 vertices, but it's not really a problem. The 1 cells are products of a vertex times an open edge. So these are open 1 cells. And the 2 cells can be squares, open squares of 2 different edges, or simplices where you get 2 configurations in 1 edge. And if you continue, you will get this way a nice filtration of the configuration by open cells. You see that conf2 is just a triangle with the diagonal removed. So it's not a triangle in the sense of CW complex. It's an open triangle. But nevertheless, you can use this. So the cells are attached along the faces, which are not diagonal, which are not at infinity. And each possibly non-compact closed K cell is properly embedded. So you need this proper embedding. When you do Borel-Moore homology, the functoriality has a small subtlety where you take proper maps. Okay, and you should have a good limit at infinity. So it contributes to a V-summand in the homology. So what I'm saying here is that you get a nice description of this relative homology with cell similar to the course you teach with CW complexes. And the relative case is similar. Now, an easy case is that if you take a genus G surface with M boundary component, you take A to be just an oriented interval. You take, sorry, it should be V. V, a representation of the surface braid group. Then the Borel-Moore homology is concentrated in a degree n, the relative Borel-Moore homology, relative to A. And we know the number of summand. This corresponds to cells in my previous description. So this one we know how to compute. And this, for m equal 1, is exactly the case which is used by De Renzy-Martel. So this easy case is known was done separately by them. And I want to finish with a little bit more structure and interesting problems. So we suppose that the boundary is decomposed as union of 2 intervals. Then we have a Poincaré duality isomorphism between Borel-Moore homology relative to minus boundary and cohomology relative to plus boundary. And similarly, if the homology, the usual homology, is isomorphic to cohomology with compact support by taking also the complementary boundary. So in this case, we are able to compute more. And if the R module V is equipped with the non-degenerate Hermitian pairing, then there exists a sesquilinear pairing which is non-degenerate. So we have intersection form, which is useful for computing. So this plays really a role, important role in Bigelow stuff. So this time I will conclude with problems. Maybe more computation. We are interested in more computation. We would be interested in understand. So we know now that there are action of mapping class group, or maybe projective action of mapping class group in certain case. We would like to discuss if this representation are unitary. We would like to extend in TQFT, to TQFT action. And of course, we are interested in the big question of the kernel of the mapping class group action. Some people would think about faithfulness. Personally, I think that faithfulness will need a slightly more involved local system than Heisenberg, but I'm not completely sure. So I will stop here.
Thank you, Professor. One moment.